Okay, the first thing I'd like to do is to work on some of the homework problems and make sure everybody's getting those and understanding the techniques to solve some of the Chapter 2 problems. So let's start with the first problem. And this is problem 2.1 from the text. It is with respect to the definition of convexity, and what it is asking, it's saying, let's suppose we have some set C, which is a subset of the vector space Rn. So Rn is the space that contains all vectors with n real values. So if it's R3, it's vectors with 3 real numbers in them. And it goes on to say that let's suppose that this set, which is a subset of Rn, is a convex set, and it's got some number of elements that are all elements of that set. So we have C is a subset of Rn. And then it says that the elements of C, we're going to call them X. C is convex. And then it gives us these numbers theta 1 through theta k. And these are going to be real numbers such that each of them, so we see theta I, so this up here is theta k. Let me write this a little better. Theta k, such that each one of them, so we'll say theta I, is greater than or equal to 0, and also the sum of all the thetas, theta 1, let's write it this way, just to be more compact. So sum of I going from 1 to k, theta I is equal to 1. All the thetas sum up to 1. And it's asking us to show that this sum theta 1 x1 delta theta k xk is in fact in this set C. And we're going to use the definition of convexity to do this. Okay, so to start this, we're going to define a function y. Y is going to be this sum of I going from 1 to k of theta I xi. So it's just simply this sum here. Now we want to show that y is in the set C. Let's also assume that theta 1, the first theta in this series, is not equal to 1. And we can do this without loss of generality, and then we can rewrite y. What we're going to do, we're going to pull the first element of this sum out. So we're going to rewrite y as theta 1 x1 plus the sum of I ranging from 2 to k of theta I xi. So now what we've done, keep in mind, note off to the side here, that if C is convex and I have two elements of C, say x1 and x2, then theta 1 x1 plus 1 minus theta 1 x2 is in C. This is the definition of convexity. So what we want to do is we want to show that this is actually this form. That's the strategy that we're using to do this proof. Okay, so we can further work on this expression for y. And we could say, well, this is going to be theta 1 x1 plus 1 minus theta 1 times the sum of I ranging from 2 to k of mu I xi. So what we've done here is where in this sum up here we have a different theta multiplying each of the x's. All we're doing here is we're saying, okay, instead of a different theta, let's make it a different mu. And how do we get that mu? Well, each mu is theta with 1 minus theta 1 factored out of it, right? So, for example, theta 2 is equal to mu 2 times 1 minus theta 1, for example. And this would hold for all of them. And if you stare at this for a minute, you will notice that mu, each of the mu's, then has to be greater than or equal to 0, because the thetas are greater than or equal to 0, and we're factoring something positive out of them. So the mu's have to remain positive numbers. Also, we can write an expression for mu I using this expression. Mu I would be equal to theta I over 1 minus theta 1, right? So just solving this expression for mu. So now we can say that the sum, so now I want to work on this part. Basically what I need to do, I know that xi, or I'm sorry, x1, I know that x1 is in the set. Okay, I know that anything of this form is in the set. So what I need to show is that this is in the set, and then I've proved it. So let's work on that sum. So now we can say the sum of I equal to 2 to the k, ranging from 2 to k, of mu I is equal to the sum of I ranging from 2 to k of theta I over 1 minus theta 1. That's just using this definition inside the sum. And since the sum of I ranging from 1 to k of theta I is equal to 1, and where does this come from? Well, this comes from the fact that we're told in the problem that all the thetas add up to 1. Then we can say from here it follows that the sum of I ranging from 2 to k of theta I equals 1 minus theta 1, and now we can use these two expressions. So the sum of I ranging from 2 to k of mu sub I is equal to 1 minus theta 1 over 1 minus theta 1, which is equal to 1. Now, we know that C is convex. We're told that in the problem, and if that's the case, then the sum of I ranging from 2 to k of mu I xi has to be an element of C by our definition of convexity. So theta 1 x1 plus 1 minus theta 1 times the sum of I ranging from 2 to k of mu I xi also must be an element of C. All right, let's look at number 3. Number 3 deals with this idea of midpoint convexity. So the definition of midpoint convexity, we'll say some set C, is midpoint convex if the following holds true. Suppose we have 2 points A and B that are in the set C, then the average, or the midpoint, of these two sets, of these 2 points, in other words, A plus B over 2 is in C. All right, that's our definition for midpoint convexity. And if a set is convex, then it's also midpoint convex. And this problem is asking us about showing that if a set is midpoint convex and closed, that it's also convex, that is, that it meets the definition of convexity. And the approach to solve this problem is a little bit tricky. So I wanted to go over this one with you. Okay, so what we are going to do is we are going to assume that, well, first of all, let's write our definition of convexity. So what we want to do is we want to show that theta x plus 1 minus theta y is an element of C for all theta on the interval 0, 1. That's just our definition of convexity. All right, and the way that we're going to do this is we're going to let this number that we're going to write theta superscript k, we're going to let this be the closest binary number to theta that I can get using k bits. The reason for this will be revealed in a minute. But what we're going to do then is we can say, well, we'll write an expression for theta to the k. We can write theta to the k like this. It's equal to the sum of I ranging from 1 to k of c sub I 2 to the minus I, where the c sub i's are the binary parts. Notice this notation, I mean the interval, this notation, I mean it's an element of this set. It's either 0 or 1. So C is either 0 or 1, and then we have the other part of the expression, which is 2 to the negative power of I. So we've got, these are all powers of 1/2, essentially. And the reason we're doing that is to deal with this 2 in the denominator here. So what you should see as we go through the problem is that this 2 in the denominator becomes very much related to this expression here. So using midpoint convexity, we can say that theta to the k x plus 1 minus theta to the k y is an element of C. And really that's it, but let's understand why we can do this. We can do this because we can iterate through each bit of theta to the k and always have something of one of the following forms. So this is because for each bit of theta to the k, we have it would either be something like, so we could have x plus y over 2. This would be the case where this was 1, right? C sub I is 1. So that would, or we could have something of the form x plus 0 over 2, or we could have something of the form 0 plus x over 2. And all of these meet this midpoint convexity idea. And then we can use these, we can start to sum these up bit by bit to build the expression that we already wrote, this one here. So we can say, okay, if we are in k bits, then by midpoint convexity, that element will be in the set, okay, at the kth bit. And now what we want to do is we want to show that this holds for an infinite number of bits. So, and that it simply does because the set C is closed. So because C is a closed set, the limit as k goes to infinity of theta to the k x plus 1 minus theta to the k y is equal to, this is simply equal to, now keep in mind this is not exponentiation, it's saying how many bits we have. So if theta to the k is the closest representation of theta that we have in k bits, then if we have an infinite number of bits, it's an exact representation of theta. So this expression simply is theta x plus 1 minus theta y. And because the set is closed, this will also be an element of C. And then that finishes our proof. Okay, let's move on to a different one. I want to look at number 2.12, and that has several parts. We'll look at a couple parts. So it's asking us which of the following sets are convex. There's a couple that are very straightforward, so we'll just go over those with you, and then we'll look at something that's a little more complicated. So the first one says a slab. So it's a set of the form x's that are from Rn, where some number alpha is less than or equal to A transpose x, which is less than or equal to some number beta. And this forms a slab. And we can simply observe that a slab would be an intersection of two half spaces. And so an intersection of two half spaces is convex. For part B, it's saying a rectangle. So a rectangle is x's from Rn, where some alpha I less than or equal to xi less than or equal to beta I. So it's sort of a generalization of the slab. And we can observe that the rectangle is an intersection of some finite number of half spaces. Remember, the slab was an intersection of two half spaces. The rectangle is generalizing it, and you can see that it's generalizing it from the form that we're given in the problem. And since it is a finite intersection of half spaces, it is in fact a convex set. Let's move down to number D. So this is 212D. And it says the set of points closer to a given point than a given set. So that is expressed as x's such that the 2 norm, so when we say closer, we're using closer in the Euclidean sense here, the 2 norm is less than or equal to the 2 norm of x minus y. So the 2 norm of x minus x0 is less than or equal to 2 norm of xy for all y in our set S. Okay, so again, this is all the x's that are closer to some given point than a given set. And here S is a subset of Rn. And we can express this set as an intersection of some number of half spaces. So we would do that like this. this set that is described here can be written as an intersection of half spaces, and therefore it's going to be convex. Here's how that would look. It would be the intersection for y's that are elements of the set S of x, such that the 2 norm of x minus x naught is less than or equal to the 2 norm of x minus y. And this is an intersection of half spaces because if you look at this expression, this is a half space. And therefore, this set is convex. Maybe let's look at one more. Let's look at letter G. So G says the set of points whose distance to a point A does not exceed a fixed fraction of theta of the distance to B. So we can write this as the set X such that x minus a, 2 norm of x minus a, the distance from x minus a, is less than or equal to some fraction theta, so theta times the distance of x to b. All the x's that satisfy this are in the set, and they also say assume that a is not equal to b and that theta is between 0 and 1. Okay, so let's manipulate this set a little bit. We can first square everything, square all our distance metrics, and square theta. So this set X is equal to the set of x's such that x minus a 2 norm squared now is going to be less than or equal to theta squared times 2 norm x minus b squared. And now we can further expand this. So this is equal to x's where 1 minus theta squared x transpose x minus 2 times a minus theta squared b transpose x plus a transpose a minus theta squared b transpose b is less than or equal to 0. And we can look at two cases that will encompass all the possible cases here. In the first case, if theta is equal to 1, then this is a half space. And if theta is less than 1, then it's a ball. And of course, in both cases, it's convex. Okay, I want to. It may not be obvious how we got from here to here. So let's just walk through that real quick. So we start off with this expression up top. I'm just going to rewrite it down here. So we've got x such that x minus a 2 norm squared less than or equal to theta squared times 2 norm x minus b squared. Okay, that's our expression up there. And now let's start manipulating that expression. So first of all, we can take these 2 norms and multiply them out. So note that the 2 norm of x minus a is equal to, so if you think about what this would look like, right, let's just say there was 2 elements in each of these. Then it would be x1 minus y1 squared. Let's just square this. We don't have to deal with the square root. Right, so it would be x1 minus y1 squared and plus x2 minus y2 squared. This is in the case where x and y have 2 elements. And so this is x1 squared minus x1 y1 plus y1 squared plus x2 squared minus x2 y2 plus y2 squared. Okay, now if we look at these terms, if we take this term and this term, we can just write that as x transpose x. And if we take this term and this term, this would be minus x transpose y. And then this term and this term give us plus y transpose y. So we can write that norm like that. So now we can rewrite this expression as follows. We will have x transpose x minus x transpose a plus a transpose a. That all comes from here. Oh, before I do that, first I should say we're going to rewrite the entire expression as x minus a 2 norm squared minus x minus b 2 norm squared is less than or equal to 0. So I'm just taking the right-hand side and moving it over to the left, and now I'll begin to rewrite the expression. So now, working first with this one, it's going to be x transpose x minus x transpose a plus a transpose a minus, and I think I missed a theta squared here. There needs to be a theta squared there. Minus theta squared times the quantity x transpose x minus x transpose b plus b transpose b. And this is going to be less than or equal to 0. And now I can start to group things that are alike. So if I factor the x transpose x terms out, I have 1 minus theta squared times x transpose x. That gives me those x transpose x terms. And then I have an A transpose A term. I'm just going to do these in an order that's going to be convenient for me in the next step, plus a B transpose B term from over here. And then the terms that remain are minus x transpose A minus x minus theta squared. There needs to be a theta squared here. Minus theta squared x transpose B. And this, again, must be less than or equal to 0. And now I'm just going to do one more manipulation. So I'm going to leave this 1 minus theta squared x transpose x for the first term. And I'm going to take this term, this theta, no, I'm going to leave that term alone. I am going to take, let's see, this term, x transpose A, and this term, theta squared x transpose B, and I'm just going to factor out the x transpose. So this is going to be minus x transpose A minus theta squared B. I just want to write it like that. This looks very quadratic in the way that it's being written. And then plus A transpose A, the remaining terms, A transpose A plus theta squared, or sorry, minus theta squared B transpose B. And all of this needs to be less than or equal to 0. And this form is this form that I wrote here. We're very close to it. I think I'm off by a factor of 2. But you can see how where these terms fall out now using this idea. I'm sure there's an error in here because I believe there needs to be a 2 somewhere where there isn't. I'm going to let that go. I'm sure you can figure out where I made the mistake. Okay, so that's the, just to try and get it all in focus, that's the idea of what is going on in order to get it into this form. And then close observation of this form shows you that you have either a half space or a ball. If you look at the form for a half space, the form for a ball, plugging in theta equal to either something smaller than 1 or to 1, it just falls into that. Okay, next I would like to look at number 2.19, and I'm going to do part A. So this is linear fractional functions. And so let's just remind ourselves that a linear fractional function looks like this. It's ax plus b. Well, let me write it. Let me be a little more complete. F of x is equal to ax plus b over c transpose x plus d. And there's a domain constraint here. The domain of this function is such that we won't get we won't get a 0 or a negative in the denominator here. So it's x is such that c transpose x plus d is greater than 0. Okay, so that's a linear fractional function. And what we're doing in this problem is we're dealing with the inverse image of a convex set under the linear fractional function. So what that means is f inverse of c, where c is a convex set, and this is equal to x's from the domain of f, such that f of x is in the convex set C. And what we're asked to do here is to give a description of the inverse image of the set under the linear inverse image under the linear fractional function for the sets, and there are looks like 4 parts to the problem, And I just want to work through the first one to give you guys an idea of how to approach these. So the first one, we're given a half space. So that it's a half space C that contains y's where G transpose y is less than or equal to H. So that's a standard half space, of course. We will restrict G from being 0 here. And we want to know what is the inverse image under this set. And I'm just going to rewrite what I wrote originally so that we can start from there. So it's x's in the domain of f, where f of x is an element of C. And here we can put, so let's expand on this. So this is going to be equal to x's in the domain of f, such that G transpose, so now I'm using the definition of our half space. So it's G transpose f of x less than or equal to H. Okay, and I can go from there. So this is going to be equal to, so I'm going to plug in now the linear fractional function itself. So it's going to be x such that, so here's G transpose f of x, but we've defined f of x here, so let's write that in. So it's G transpose ax plus b over C transpose x plus d, there's our linear fractional, is less than or equal to H. And of course we need to now include the domain constraint C transpose x plus d has to be greater than 0. And we can manipulate this to get it, what we're going to do is manipulate it so that we can see that it turns out to be another half space. So first thing I want to do here is I am going to multiply through the G transpose here. So it's going to be x's such that G transpose ax plus G transpose b over C transpose x plus d is less than or equal to H. This domain constraint is just going to carry through. I'm not going to keep rewriting it. We'll just assume it's in every line. And now I'm just going to manipulate this equation. So this is going to be x such that G transpose ax plus G transpose b is less than or equal to H times C transpose x plus d. So I'm multiplying both sides by C transpose x plus d. And now I'll multiply through. So this is going to be G transpose ax plus G transpose b less than or equal to H C transpose x plus HD. And now I want to get all the x terms on the same side. So this is going to be x's such that G transpose ax minus H C transpose x, moving this guy over, is less than or equal to, and then I'll put all these other terms. These terms are going to be constants, G transpose b plus HD on the right-hand side. And now I just need to manipulate this a little bit further, and it'll become very obvious that this is a half space. So this is going to be x's such that what I'm going to do is I want to factor out the x here And I'm also going to write this as a vector transpose times x. So I'm going to reverse the order here. Let me write it and then I'll explain it. So what I'm going to write is it's A transpose G minus HC transpose X less than or equal to HD minus G transpose B. Got a sign error here. G transpose B. So what I'm doing here is that using the idea that let's say AX is equal to X transpose A transpose, right? Just using that to get this into this form. So now what we have here, this is a vector transpose times another vector less than or equal to some constant, and that's the definition of a half space. All right, so I want to move into Chapter 3, Convex Functions, and begin the discussion there. So let's start out by with a definition. So suppose we have a function f that is going to be a mapping from Rn onto R. Then we say this function is convex if two things. One, the domain of f is a convex set. And the following holds. F of theta x plus 1 minus theta y is less than or equal to theta f of x minus 1 minus theta f of y. Notice that here, this is a convex combination of x and y on the left-hand side. And here what we're saying is that we are evaluating the function at a point on a line segment between x and y. And this has to hold true for all x and y in the domain of f, where theta is constrained to be between 0 and 1. So for example, if we have a function that looks like this, and this point is at f of x, and this point is at y, f of y. This is the line segment between those 2 points. And that line segment, everything on that line segment, this line segment basically lies above the function itself. Now, we say that f is concave. If minus f is convex. One thing to note with respect to a convex function, for example, is that the function can be decreasing monotonically but is still convex. And the reason why it's convex is because it has positive curvature. Further, we say that f is strictly convex if f of theta x plus 1 minus theta y is strictly less than theta f of x plus 1 minus theta f of y. Okay, so up here in our original definition of convexity, we have less than or equal to, but for the strictly convex function, we have less than. Okay, so let's consider a function on an interval defined by the points x1 and x2. So if we have our function starting here at x1, then we'll trace out the function. So that point is x1. And we're going to take a point here, and we're going to call it A. And another point here, which we'll call B. And then the end of our interval is here. So that's x2. And I'm going to connect A and B with a line segment. So along this line segment, we have points that are defined by 1 minus theta f of A plus theta f of B. For example, this point is one of those. And then we can talk about the point straight down from that, which would be f of 1 minus theta A plus theta B. And what the definition is telling us is that all the points along the line segment AB must lie above the points on the function f in the domain defined by the interval. Okay, so wherever I choose these points A and B to be, if I connect them by a straight line, then in between those 2 points, all of the points for the function must lie below it. Let's look at some examples. Of convex functions. Affine functions. Ax plus b on R for all a and b are affine. These are linear functions plus a constant. They have zero curvature. And notice, so these are linear plus a constant. Zero curvature. And notice that for an affine function, f of theta x plus 1 minus theta y is actually equal to theta f of x plus 1 minus theta f of y. So this is not a strictly convex function, but it's convex, and it's also concave. The affine functions are the boundary of the set of convex functions. Another example is the exponential function. E to the xt, for example, for any constant t that is real, that will be a convex function. Powers, x to the a, defined on R++, that's the domain, for a greater than or equal to 1, or a less than or equal to 0. If a is between 0 and 1, then we don't have a convex function. Powers of absolute values. Slightly different domain here. So this would be the absolute value of x to the a on R for a greater than or equal to 1. And then another one, so these are all probably functions that you've dealt with before, but there's a function. The entropy function is minus x log x, and the negative of the entropy function, x log x, so negative entropy, which is x log x. This is defined on R++, and this is convex. The function looks like this. Roughly has that shape. So those functions are all convex. And equally important are the concave functions. The affine functions, as I mentioned before, are both convex and concave. They're right on the border between the two. Powers, x to the a, on R++, but now where 0 is less than or equal to a, less than or equal to 1. So if the exponent is between 0 and 1, we have a concave function, and log x on R++ is concave. Notice that these are things like square roots. So all those examples, these are examples on R. These examples of convex and concave functions, but we can also have examples from Rn and from Rm by n, right? So examples of convex functions on Rn and on R m by n, right? Where m by n, this is the set of m by n real valued matrices, and this of course is the set of real valued vectors with n elements. So from Rn, an affine function in this case, it would look like f of x equal to a transpose x plus b. And this, again, is a general linear function on Rn. and it's both convex and concave. And in fact, it's straddling the border between convexity and concavity. The affine function. Also norms. So we talked about norms before. So the p norm of x. And I'm not sure if I gave you this general formula before, but general formula for a norm is I ranging from 1 to n. X sub I to the p, and that whole sum to the 1 over p, and this is for p greater than or equal to 1. And this p can go up to infinity, right? So the 2 norm, the Euclidean norm that we're most familiar with, would be the 1/2 power here, so it would be the square root of the sum of the squares of the elements of x, but then we generalize that to a p norm. So these are p norms, where p can be anything greater than 1, and the infinity norm of x is defined to be equal to the maximum entry in x. In general, some of the things that define a norm, they must have a homogeneity property. And they must satisfy the triangle inequality. And actually, the fact that they must satisfy the triangle inequality is what leads to the convexity proof for norms. Although in general, the proof that a norm is convex is not a trivial matter. Moving to functions on R m by n. So again, these are the m by n matrices. Once again, we have the affine functions. So capital X here representing it's a matrix, and this is going to be, this affine function is going to be defined to be trace A transpose X plus B, and this is equal to this double sum across the rows and the columns like that. You'll also see this written as like an inner product of A and X, or you may see it written A dot X, right? So this is a standard inner product on matrices, and it's defined as the trace of A transpose X. So much like we generalize the idea of inequalities, we're generalizing the idea of an inner product as well. Spectral norm. You may also hear this being called the L2 induced norm. F of x is equal to this spectral norm of x, which is equal to sigma max x, which is equal to lambda max x transpose x square root. So it's the square root of the largest eigenvalue of x transpose x. Okay. A useful concept for establishing the convexity of a function is to restrict that function to a line. So let's discuss that a little bit. So suppose we have function f mapping Rn onto R. That is a convex function. And we can say that this function is convex if and only if the function g is a mapping from R to R. So a function is convex if and only if it is convex when restricted to any line, where, so we'll define these functions now. The function g is equal to f of x plus tv, and the domain of g is t's such that x plus tv is in the domain of f, and this is, so f is convex if and only if g, which is a mapping from R to R, where it is f of x plus tv, where the domain of g are t's such that this argument is in the domain of f, so this needs to be a valid expression, and f is convex if this is convex in T for any x in the domain of f and V in Rn. So we can look at an example of this using the log determinant function. So let's take this function f, which is mapping symmetric matrices onto the reals, where f of x is equal to log det x. So this is the log of the determinant of a positive definite matrix. Positive definite matrix because we are restricting the domain. There's a domain restriction here that it's a positive definite matrix. So we're taking the log of the determinant of a positive definite matrix. This is actually concave. So we want to restrict this function to a line, and so we need to think about some idea of what is a line in positive definite space. Okay, so we need a line in positive definite space. So let's define our function g of t. G of t is going to be equal to, well, if we look at what it was, it's f of x plus tv, and x is log det x, so it's going to be log det of x, remember x is a matrix, plus tv. And so if we think about what we have here, we believe at this point log det to be a concave function. So we want to show that this is concave. This is a function of t. We need to show that to be concave. This x is a point in positive definite space, and this tv is its t multiplied by some direction v, where V is a symmetric matrix. So if you think about what we're doing here is we're picking a point in positive definite space, and that point is a matrix X. Okay, X is a symmetric positive definite matrix. And then we're adding to that multiples of some other symmetric matrix. So if I have a positive definite matrix and I add a symmetric matrix to it, I get another positive definite matrix. And if I keep adding multiples of a positive definite matrix to it, I'm moving through some linear direction in positive definite space. So that's what this is doing. So now I can rewrite this. This is equal to log det x plus log det of I plus t x to the minus 1/2 v x to the minus 1/2. I'll derive that shortly. This is equal to log det x plus the sum of I ranging from 1 to n of the log of 1 plus t lambda I. Where these lambda i's are the eigenvalues of x minus 1/2 v x minus 1/2. And we see that g is concave in t. Therefore, f is a concave function. So I want to go through a little bit of what comes in between here. So let me rewrite the function g of t. So g of t is this function log det of x, our starting point, plus tv, our direction through a positive definite space. And x is positive, so it has a square root. X plus tv is equal to x to the 1/2 times the quantity I plus t x to the 1/2 v x to the 1/2 x to the 1/2. And if you just multiply this through, you'll see that this is in fact true. Remember, the t is a scalar. So from here, we can write g of t is equal to log det x 1/2 I plus t. So these are negatives up here. X minus 1/2 v x minus 1/2 x 1/2. And we use the property of the determinant, that the determinant of a product is equal to the product of the determinants. So from there, we can rewrite this as log det x plus log det I plus t x minus 1/2 v x minus 1/2. And then if we take the Eigen expansion of this, in other words, we're going to take this matrix x minus 1/2 v x minus 1/2, and we're going to express it as q lambda q transpose. So let me write this, and then I'll explain exactly where it all comes from. So we're going to say that this is equal to log det x plus log det of I plus t times q lambda q transpose. Okay. So if we take this matrix, this is a positive semi-definite matrix. There's a positive definite matrix. It's going to have real eigenvalues. It's going to have real distinct eigenvalues. Since it has real distinct eigenvalues, we can write this matrix, or any matrix that has real distinct eigenvalues, we can write it as q lambda. Let's say this. Let's just go off to an aside here for a second. If x is positive definite, this works for other matrices that aren't positive definite, but it will work. Is guaranteed to work for matrices that are positive definite. Then x is equal to let's say I want to use let's say, well, I already used V, I've used S, well, we've used Q, I don't want to use Q. All right, let's just say M lambda M inverse, where M has columns that are the eigenvectors of X, and lambda is a diagonal matrix with the eigenvalues along the diagonal. That gets us to M lambda M inverse. Now, if X is positive definite, then the eigenvectors can be chosen to be orthogonal. And if they are orthogonal, then the inverse is the transpose. So that's where we get Q lambda Q transpose. Q is an orthogonal matrix. The columns are orthogonal, so its inverse is its transpose. So that gets us to that point. Okay, and I can write, notice that Q transpose, because of the same property that I just discussed, right, that the transpose of Q is its inverse because it is an orthogonal matrix, then Q transpose equals I, so I can rewrite this as log det X plus log det Q transpose for I plus T Q lambda Q transpose. And this is a diagonal matrix. So, if I have a diagonal matrix, the determinant is equal to the product of the diagonal entries. So now I can rewrite this as log det X plus the sum of I going from 1 to n of the log of 1 plus T lambda I, where the lambda i's are the eigenvalues. This is lambda. Are the eigenvalues of x minus 1/2 v x minus 1/2. Okay, so now we've gotten into that expression. And this has negative curvature. Okay, so this is a very simple code, but
if you want to download it, it's on my GitHub, so you can find it there. But the idea here is that we're going to show, we're going to use this log_det concavity idea with this MATLAB script. So first thing that we're going to do is we're going to generate random positive definite matrices, and then we're going to test that log_det is concave by restricting the function to a line in positive definite space. So exactly what we were just showing by example, or analytically, what we showed analytically, we're going to do that numerically now, right? So the first thing I do is I generate a random 3x3 matrix, doing it for 3x3s. You can change this if you want and do it for any size you want. Then I make that a positive definite matrix by multiplying by its transpose on the left. So random matrix transpose times random matrix. I define the parameter t, right? This is the parameter that's going to allow me to move along a line in positive definite space. And then I define v. So v is v is a symmetric matrix. In our proof, it was a symmetric matrix. It's going to turn out to be positive definite symmetric because of the way I'm making it symmetric here is also going to make it positive definite. But keep in mind that v does not have to be positive definite. It just has to be symmetric. So our starting point is a positive definite matrix, and then we're going to move along a line. If you can think of the idea of the slope of a line in the space of positive definite matrices, then the slope of that line in some sense is v, and the slope doesn't have to be positive definite. It just has to be such that when I add a multiple of v to my starting point, I get another symmetric matrix. So it has to be symmetric. Then what we do is we evaluate the function g of t, right? So g of t was defined to be log_det x plus tv, where x is the thing that we're testing, right? Which in this case is going to be the random positive definite matrix up here. And we're going to do this 100 times and plot it. Okay, so that's the deal. I'm just going to, just going to copy that. I've got MATLAB open over here. And let me have a script. And I'll paste it in. It's going to ask me to save. It's odd. Okay, and we see that this is concave, and I think maybe what I want to do here, let's try that. Okay, So here we're generating all of these functions, and they are all concave. So we did 100 of them. Of course, this was random. If we do it again, it'll be different. We're not proving the convexity here. We're demonstrating, or the concavity. We're not proving that it's concave, right? Because we're just, we haven't tested every line. We would need to prove it in general, but this is a demonstration of what we were just showing, as I said, analytically.